Here we're looking at a problem from the oscillations unit. This is from a 1984 AP Physics multiple choice section, a two-part question. I chose this because it was commonly answered incorrectly when I would give it to my classes, and I thought it served as a good overall view of a vertically aligned spring problem, something you see fairly often. So this block is connected to an initially unstretched spring. As we release it from rest, it will bob up and down, and we are looking for the amplitude of its simple harmonic oscillation, and then we're looking for how long it takes for the block to go all the way down and come all the way back up to its initial position. First thing I'll do is establish some key moments. Moment A will be when the block is first released, and then moment B will be the lowest part of its oscillation right before it's about to come back up, and I will set moment B as my reference point, or where a height of 0 exists. As I think about attacking energy for this problem, I should establish a system. My system will be the spring, the block, and Earth. Let's look at some graphs that visualize what energies are present in our world. At moment A, we have a height above our reference point, so that there is a gravitational potential energy in our system. There's no kinetic energy, since it is released from rest, and there's no elastic energy because the spring is not stretched yet. When we get to moment B, we have lost our gravitational energy. We're at a height of 0. Again, no kinetic energy because we're not moving at the bottom. We're about to go back up, so the velocity is 0 at this moment. But we do have an elastic potential energy because the spring is now stretched and it's about to pull the block back up. I can't think of any other energies in this world. There are no external forces doing work, so I know that these energies are equal. I'm showing that with my bar heights, and I'm going to show that mathematically with an equation like this, conservation of energy. From there, I look at my formula sheet. Two equations will help. I've got my elastic potential energy formula and my gravitational potential energy formula. So I sub those in. Now something to note is the variables h for height and delta x for stretch of spring. If you look at the picture, this orange bar will represent the length for both of these variables. This is not only the height that the block changes from A to B, this is also how much the spring will stretch from its initial location down to its final. So what looks like two variables is actually the same variable, and so I'm going to cancel one of those out because they're the same variable. So here is what remains. Now I'm just plugging in the given information from the problem. I know everything except delta x, the stretch of the spring, and I can do the algebra to solve for that. So this answer represents how much the spring has stretched from A to B. Many students end here, they select choice B, and they get this one wrong. Well, be careful. The stretch of the spring is not necessarily the amplitude. We want to define amplitude as being related to the equilibrium position of the block, right in the middle of its oscillation. Amplitude is defined as the length from equilibrium to the maximum displacement, so we would be solving for the length of this purple bar, and that is exactly half of the total stretch from A to B. So we want to take our answer, divide it by 2, we wind up with 1 over 40 meters, and that will be the answer to question 1, choice A. Now we'll look at question 2. Conceptually, we need to understand what a period is. This is the time that it takes to complete one full oscillation, and since in question 2 it is referencing that we will return to our initial position, that means we've completed a full oscillation, and we will be solving for the full value of the period. My formula sheet says that the period for a spring oscillator we can solve for with 2 times pi times the square root of the mass connected to the spring divided by the spring constant. Well, those are all numbers that I know. The mass, the spring constant, I always know pi, and so I can solve for the period of the spring oscillator here. Plugging that in, I've got 0.1 times pi. If I look at the answer choices, that would be the same as pi divided by 10, and so I'll choose choice C for number 2. So to summarize this one, oscillations are a good connection to energy, so make sure you're considering your energy flow graphs like I did with number 1, and then make sure you know the definition of key terms. In this example, amplitude and period were important to know. If you found this video helpful, then I have other resources that you may be interested in as well. For more information, check out my website, shoot me an email, or follow me on X and Facebook. All of the links can be found in the video description.